Hello everyone and welcome back to High Performance Computing Advanced Scientific Computing course, Lecture 9 CFD and Parallel Computing in second part. In this part, we will have some detail how doing the parallel computing setup, and then we'll have some example in the CFD and how high performance computing it's essential and could improve the CFD solution. Regarding the parallel computing in CFD, let's have the example from the heat transfer. Here is the problem domain from the CFD, and we solve this on the large grid. We assume we have 20,000 by 20,000, so the storage requirement it will be here the grid point, and we have 8 bytes per number. Then the number per node, which is 2D, we will have 6.4 gigabyte requirement for these domain of the problem. We can split this domain to 6 smaller area, and we send these 6 domain among 6 processors to doing the parallel computing. We should specify for 2D and 3D problem, it is necessary to exchange line and planes of data. Each processor updates the portion of the grid that reside on that node and swap data with the neighbors. However, usually the grids must have an overlap because it's taking some updated information from the neighbor grids. And this is very simple presentation of the parallel computing for the domain in the CFD. In parallel computing for CFD, when we have a complex problem, we must determine how the processors are connected, how to prepare the data to be sent if it's not continuous in memory, how to transfer the data in the right order so the data is there when needed. From the previous lectures, we had the MPI. In message passing, the processor explicitly send and receive data. The generated form is we have the send and receive with some detail. In actual implementation, the arguments are slightly more complex due to the need to deal with data that is not continuous in memory. If we look on the structure of the program, we have these detail. We need to initialize the parallelization, determine the setup, including number of processor and connectivity. If we are applying master, we should determine the size. We should specify the broadcast parameters, and when we specify the time steps, then we will finishing the computing. We gathering the data from all processor computing and then finishing the parallelization. How we measuring the parallelization was successful? We have the speed up with this definition, which is time for one processor over the time for p processor. The perfect speed up with this nomination is t to n, which is leading to the speed up. Usually the performance decreases as n increase, which is described in the part of the we had lecture on the speed up and scalability. Here is a recap for MPI. We had lecture for it. in the first part of the course. As we know, MPI is a library, not a language. It consists of subroutines that are called from Fortran, C or C++ programs to facilitate parallelization of programs. MPI is a specification, not a particular implementation. All parallel computer vendors currently offer MPI implementation for their machines. MPI is designed for the message passing model. If we look on the general structure of the MPI program, we have the initialize MPI and then identity of each processor, then number of the processor used. We're adding the actual codes in this part and then ending the MPI. We can run same program on all processor, just set up problem on master processor by this setup. Let's have a look on the setup for MPI in CFD. If we look here, we have 4 steps. First, we need to exchanging the data. Data transfer need to be synchronized from this available command. Then we need to send information to all processor, which is broadcast. Send and receive the information. In the third step, we set up the communicator for a Cartesian grid. And in 4th step, we have the timing for the program. We can have several graphics-based program can be used to analyze the performance of the code. However, regarding the derived data type, when data is not continuous in the memory, MPI allows us to set up derived data type. The simple one is when we send every nth element of a vector. So this is a general step to doing the setup on the MPI to applying the CFD. And with the available code, we can add the code for the program on the MPI and solving the CFD problem in the parallel computing. So far, we had a discussion about the turbulence flow detail and why it's essential to have a numerical solution for this phenomena. And then we understood that there are 3 well-known methods for turbulent flow: runs, LES, and DNS. And then we came to this point that to solve LES, it's essential to have a parallel computing. Here we have 2 examples from the heat exchanger equipment, which is this CFD simulation is done on the mirror supercomputer from Oregon National Laboratory, and this machine was with high rank a few years ago. In this simulation, the left side model take 12 hours with 6 hours to mesh and 6 hours to run with 16,000 core. The right hand side simulation with similar setups take 3 days to the result, which mostly take a time for meshing. So from this time of the computing with this number of cores, we can recognize how much the parallel computing and HPC is essential. Now let's have some more example about how we can increase the efficiency, or sometimes why we have to use LES instead of runs or DNS, and which without high performance computing we cannot reach the solution. This is an example for a tank which is refilling, and for the refilling there is a simulation with LES and runs to do the comparison with the available experiment. From the solution of the runs here, we can see the green line is from LES and the red line from the runs. As we can see, in some ports they are not matched, and the difference between them in the sum detail, when here we have the exacs or we have the incoming jet, it's providing more detail from the LES, which cannot captured by runs. But from previous point, we know runs about 10 to 5 times cheaper than LES. But it seems for some problem we cannot have a reliable solution from runs if we need much more detail, not only focus on the main features. Also in this report, there was a point that when they changing some element on the geometry, runs could not capture this detail and presenting similar result like before the change on the geometry. However, LES presented the change. That means in some problem, runs could not provide the detail and we have to apply the LES. The another example here is the DNS solution and runs for sublaminar drag in curved pipe flow, which is presenting when they're using runs with higher turbulence, the 10% of the drag reduction, which is not correct. And this is the another example which presenting DNS provide the correct result. However, DNS has some deviation, and in this kind of the problem, it seems we need to use the DNS or LES. Here is another example from the range of the scale at top dead center for the ignition timing in the combustion engine. As we can see here, when the compression is happening in the engine from 180 degree to 225 and 270 and then 306. In the top of the cylinder head, when we look on it, we can see with 270 degree and 346 degree how much we have different on the scale. Here the scale are too small. If we assume using the LES, which is filtering some scale, we can't capture this detail from the simulation. But when we're using the DNS, we can see all the detail and all scale from these simulations. And since this is related to the temperature and heat transfer, and in this kind of the problem, we need this detail. It seems it's essential to applying the DNS. And of course, it's presenting exact solution with much more detail. The another example is the DNS of a flow around a NACA 4412 wing profile here. This simulation it's made with Reynolds with 400,000 and with angle of attack 5 degrees, which made 3.2 billion grid points, locally structured data, and global unstructured mesh. When we look here on this simulation, with much more detail. Here we can see from the DNS, and it's presenting all scale size of these simulation. However, if using the another method, runs only presenting the average, and LES is filtering the smallest scale. If you want to look on the history of DNS, we can say the large eddy simulation and direct numerical solution rely on very little modeling. And therefore they are able to capture many features of turbulent flow. These approaches require simulation of a broad range of the scale, and their success is largely tied to that parallel computing. Then the parallel computing is essential to have this detail of the turbulent flow when we apply DNS or LES. And from these few examples, we saw how the difference on the detail of the solution could be captured by the DNS in contrast to other two methods. Regarding the CFD and parallelism, we can have relatively deep consideration. That's how we can improve the solution. One of the option is high order with the method. It could made a reduction in problem size, and hopefully we can reduce the cost. About the solver, with a coarse grid solver, it's a big challenge for parallel computing. And what about the parallelism? How much more parallelism could be help the solution? Regarding the high order method, there is a statement that it's efficiently deliver small dispersion errors. One of the examples for how the method is a spectral element method, which it's a variational method similar to finite element method, and the domain partitioned into E high order hexahedral elements. Trial and tens function represented as nth order tensor product, polynomial within each element n to 4, and sometimes maybe 15. Therefore, we need the fast operator evaluation for the storage and for the work, and it's converge exponentially fast with n for a smooth solution. This description example for the method provide us that choosing the high order method could be leading to accurate solution and maybe make it faster. How about the direct numerical solution? Let's have a look on the example. Here this is an example which had 3.9 million elements of order 6. There are 840 million points, and with setup on the 131,000 core, it takes 100 hours to run this simulation. But how we can run it faster? With better algorithm, like lower order for discretization, or faster solver, like lower iteration counts, or more parallelism. These are challenges to choose the correct one to solve the CFD problem and how we can make it faster. Here is an example to see how the scaling could work with parallelism. The simulation has 3.9 million elements, as we said. The max value of P is 3.9 million. If we use N over P, we will have 216 points per processor. This is the base of the number of processors of the mirror supercomputer. Is too low. Why this number is too low, 216? About the analysis that suggests the minimum of the N to P is 2000 points per MPI rank on mirror to realize 50% parallel efficiency. For any finite difference of volume or element codes, this is the suggestion. The current simulation is at N to P is 840 million over 262,144, which is lead to 3,200. So we said the minimum N to P it should be 2,000, but here we have 3,200. When we look on the parallel efficiency and the time per step, here we have the scaling beyond 1 million processor when we are applying 1 million. So we have 217 pin problem with order 9 and element 3 million. We have 2 billion points and 524,000 and 288 cores. We can do it with 1 or 2 rank per core. Here the result is showing us the red line for 1 processor per core and the green one for 2 processor per core for the time of the solution, and the blue one is the efficiency with 2 processor. We can see when we increasing the number of the processor from 1 to 2 on the core, the time step is reducing. However, the efficiency with 2 processor per core, the efficiency it's going down to 60%. So that means we have 60% parallel efficiency at 1 million rank and 2000 points per rank at 1 million rank. This is the presentation of the example of them when we are doing more parallelization and how it looks like in the result. Here are some points regarding the GPU and CFD. In the CFD, we have a concern about N sub half, which is related to the time. It's the value of N or N to P where the node performance reach half its peak for your application. Assume we have a time step. When we have half of the time step, it's mean N sub half. In addition to communication overhead, N sub half sets the strongest scale limit on complex nodes. So it is essential sometimes we have a small time step. With a small time step, it's of course a GPU accelerate the solution and we can overcome on these issues. Example of the high N sub half, this is the electromagnetic code on GPUs of Titan GPU. We can see here when the number of the GPU increasing from 1 to 4 to 8 with number of grid increasing the number of grid, the time of the calculation reducing. So that means GPU has a direct effectively advantage on the solution, and with high N sub half, GPU could help to reach the solution with fast computing. From these few examples and the talk about the turbulence flow, then the available numerical methods, we can understand now if we can apply vans instead LES, we can save 10 to 4 to 10 to 5 times cost, and as well regarding the PDEs, discretization can yield to 10 times saving and fast solver 10 to 100 times. However, the HPC, we need to examine the communication cost to see how it's making the performance better in the solution. If we want to have a general view from this discussion, we figured out the turbulence flow is applicable in the industrial and natural application. However, to understand this phenomena, we don't have a general analytical solution because of the many unknown. Therefore, we have the first option, the mean or average feature in the turbulence flow, which leads to Reynolds average Navier-Stokes runs method. In this method, we're focusing on the mean feature of the flow, and we can have average solution and only rely on the average information. If we are going to detail, we have the large eddy simulation, which large eddy simulation, LES, it's making filtering and capturing the information from the large scale or eddies, and for the smallest model we need to use SGS model. The exact solution could be achieved from direct numerical solution, which is costly, and it's extract the information from the mean feature and from the fluctuation feature, and it's able to solve it exactly, which is matched with the experiment measurement. However, it's very costly, and for real problem with massive data, especially when it's 3D, is need to spending high cost in the high performance computing to be able to solve this type of simulation. From this view, it seems there are two main option application: RANS, which is mostly applied in the industry, and for some industrial application which has some detail that is required to capture, but RANS could not be able for that. We can use a LES. However, is 10 to 5 times costly than the RANS. And also in the research on the CFD, the LES could provide us the more required information, basically on the large scale, and it's filtering the smallest size. Here we finished lecture 9, CFD and parallel computing. In this slide, you see a screenshot of the video with the available link on the references, wind turbine simulation and its animation, which is presenting how high performance computing could be helped to understand some obstacle and unknown on the wind turbine simulation. Since the wind energy one of the most interesting resources currently, and in many countries they are focusing on it, with hope HPC could develop this industry and overcome on some obstacle to make it more efficient. I suggest you watch this video. Thank you. We will back in next lecture, and we will have more example and application of the high performance computing in the computational fluid dynamic area. Thank you. Bye.